Today is the first seminar of Mr. Saifullah Jamali. So, we are starting our session with the recitation of Holy Quran. So, I am reciting few verses from Holy Quran. Auzu billahi minash shaitanir rajim. Bismillahir rahmanir rahim. Qul huwallahu ahad. Allahus samad. Lam yalid walam yulad walam yakul lahu kufuwan ahad. So today is the first seminar of Mr. Saifullah Jamali. He is doing MPhil under my supervision, Dr. Naik Mohammed Sheikh, and co-supervision of Wasim Ahmad Bhatto. The title of the seminar or his dissertation is Spectroscopic Analysis of the Lithium Fluoride Sample Using Laser Ablation. So this session is chairing by Professor Dr. Yar Mahmood Khawar Sahab. So please come forward, Saifullah, and present your work.
Bismillahirrahmanirrahim. My name is Saifullah Jamali. Today is my MPhil seminar on the topic of spectroscopic analysis of lithium using laser ablation. Under the supervision of Dr. Naik Mohammed Sheikh, Professor, University of St. Jamshoro, and co-supervisor is Dr. Wasim Ahmad Bhatto, Assistant Professor, University of St. Jamshoro. So this is the outline of my research work. One is known as motivation. Second is LIBS, laser-induced breakdown spectroscopy, experimental setup, plasma parameters, and conclusion. So this is the motivation. The aim of this work is to analyze the varieties of lithium fluoride sample using laser-induced breakdown spectroscopy, to study spectroscopic analysis of lithium fluoride sample. So this is the introduction of LIBS. Basically, LIBS is stands for laser-induced breakdown spectroscopy. LIBS is an analytical method by which one can determine quantitatively and qualitatively elemental composition of different samples. Sample may be solid, liquid, as well as a simple. So this is the overview of LIBS process. There are three main parts of LIBS process. One is known as a plasma generation. Second is known as a light collection, and third is known as a spectral analysis. So in a plasma generation, when a laser light passing from focusing lens, it interacts with the material. So as the laser light interacts with the material, plasma is generated. Finally, plasma becomes cooled down and emits radiation. Basically, radiation are known as characteristic radiations. So this process is known as a plasma generation. In the second part, there is a light collection. So there is a device known as a spectrometer. This collects light radiation emitted by plasma. So a spectrometer converts these radiations into elemental signals, electrical signals. So this is a spectral analysis. Here x-axis. So this x-axis represents the wavelength, and y-axis represents intensity of the transition lines. So LIBS process can be classified into three separate regions. There is again three important points. One is known as a laser material interaction. Second is known as a laser plasma interaction, and third is known as a plasma expansion. In a laser material, so this process is known as a laser material interaction. So as the laser interact with the material surface, plasma is generated. You may see here. So this plasma remains here in a nanosecond. While there is another laser pulse comes in a picosecond and interact with this plasma. So this process is known as a laser plasma interaction. Finally, high pressure is generated in this plasma, and plasma become expanded, and this is known as a plasma expansion. So these are the names: laser beam and plasma. Material ablation. So there is a laser pulse interact with a sample material, and plasma is generated. So this material ablation depends on two properties. One is known as a laser property, and second is known as a plasma sample property. So laser property is subdivided into 3 points. One is known as a laser width, pulse width. So this is the pulse width. the space between this point, wavelength, this is a wavelength, and irradiance. Irradiance basically is energy transfer in a per unit area is known as a laser irradiance. So simple properties is divided into 2 points. One is known as the optical property and second is known as the thermodynamic properties. Threshold fluence. For the formation of plasma, the laser fluence should be greater than latent heat of vaporization. From the literature review, the threshold fluence is estimated as FTH. Basically, FTH is a threshold fluence that is equal to rho LV radical K TE upon rho Cp. Here rho is a density of a target material in which plasma interact. LV is the latent heat of vaporization. K is the thermal conductivity of a material. TE is a laser pulse width. And Cp is a specific heat of this material in which laser light interact. So optical properties of a target material. Reflectivity of laser light from the target material sample depends on the optical property of a material. From the literature review, link is given here. Epsilon omega, that is equal to 1 minus omega p square upon omega square. Omega p is equal to radical 4 pi e square upon m into n e square. If we put 4 pi 3.14 charge of electron and mass of electron, we get this whole factor as a 9 into 10 power 3. So omega p is equal to 9 into 10 power 3 radical Ne, where omega p is the plasma frequency, omega is the laser frequency, and n is the electron number density. So this equation shows that if the plasma frequency is greater than laser frequency, so we get here negative value of epsilon E, epsilon omega. Shows that there is a reflectivity creates in a material. So thermodynamic property of target material. The values of average temperature as a function of laser and target plasma is given here. So average temperature, that is equal to radical 2 by pi Ia radical ATP upon chi, where A is equal to chi upon Cp into rho. Here Ia is the absorbed laser intensity, which is measured in power per centimeter square. A is the thermal diffusion coefficient, which is measured in a centimeter square per second. And Tp is basically laser pulse duration, which is measured in a second. This is basically time. Chi is the heat conduction coefficient. This is measured in W upon Cm. Cm is the centimeter, W is the watt, into K. K is the Kelvin. So Cp is the specific heat, which is measured in a joule per gram into Kelvin, and rho is the density of a target material, which is measured in gram centimeter cube. So the creation of plasma on a lithium fluoride sample using laser induced breakdown spectroscopy. This is a basically closed image of plasma. So when a laser light interact, here is a reflecting glass, and laser light change its direction and passing from this lens. Basically this lens is a focusing lens. We say this is a convex lens which is used to focus laser light. As the laser light interact with this material, plasma is generated. So this is a spectrometer device which collect this light through optical fiber glass. So mechanism consists of ionization, how plasma is generated, what is physics behind this. So this ionization consists of cascade breakdown. Sometimes it is known as the impact ionization. So when an electron absorb energy, so this energy is basically laser energy which interact with the material surface. So electron getting energy, this become energetic electron, and energetic electron interact with another atom, and atom become ion, we get 2 electron. So this is a reaction. H mu basically is the energy of photon. When interact with the electron, we get a energetic electron. This is energetic electron, and this energetic electron interact with the metal surface. This is atom, and atom becomes ion. We get 2 electron. So on a time scale, it grows electron number density exponentially. So this is the same process, cascade breakdown. So when a photon interact with this atom, electron, this electron ejected from atom and transfers some energy to this electron, and this electron is also ejected from this atom. So we get 2 electron and atom becomes ion. Reaction is also given here, and this process increase exponentially. So second is known as the multi-photon ionization. In multi-photon ionization, there are number of photons having multiple energy interact with atom. Atom become ion, we get an electron. So this is the reaction is given here. There are number of photons having energy h mu interact with a neutral atom, and atom becomes ion, we get an electron. So on the time scale, it grows electron number density linearly. So second is known as a recombination. When plasma is generated, plasma become recombination as the light emitted. So this is a recombination method. When an ion capture electron, so this become atom. There is a neighbor electron. The energy emitted from this process is getting this electron, and electron become energetic electron. Finally, energetic electron emits light. So this is a basically light, as we seen before, how plasma emits light. So this is a reaction is given here. Electron plus ion making neutral atom, and there's a neighbor electron which getting energy, this becomes excited electron. So same reaction is also given here. Rate of 3-body recombination is directly proportional to Ne. Ne basically electron number density square, Ni ion number density square, which is created in plasma, and electron temperature power minus 9/2 log of Z bar square plus 1. Second recombination is known as a radiative recombination. Capture an electron. When ion capture an electron, this become atom, and we get energy. This become light energy. This is basically. So here electron interact with a neutral atom, ions. Ion become atom, and we get a energy having frequency equal to h mu. The rate of recombination is directly proportional to Ne. Ne basically electron number density. Ni, it is basically ion number density, electron temperature power minus 3/4. So this is the inverse Bremsstrahlung, which is also happening during plasma generation. So when a photon interact with an inner shell electron, this electron ejected from this material. So we get energetic electron. So this is a basically Bremsstrahlung, inverse Bremsstrahlung. So advantages of LIBS. LIBS basically stand for laser induced breakdown spectroscopy. Advantages of laser induced breakdown spectroscopy are given below. It offers rapid analysis, require no simple preparation. We have already simple prepared. Require no contact with the sample, sensitive to all elements. The analysis spot size is small, work in a hostile environment, and finally scalable in a sample size. So this is the applications of LIBS, laser induced breakdown spectroscopy. The applications of LIBS, laser induced breakdown spectroscopy, are given here. There is a material applications, industrial applications, environmental applications, biomedical applications, military and safety applications, agriculture applications, as well as remote analysis. So this is the experimental setup. We say this is a research methodology. This is the experimental setup. So this is a laser device which produces laser. This is the source of laser, power supply, trigger signal, delay generator. This is a laptop, spectrometer, optical fiber wire, and target sample, focusing lens, and this is a reflecting glass. So when a laser light passing from this source, laser source, it interacts with the reflecting glass. When this laser light interacts with the reflecting glass, it changes its direction by 90 degree, and after passing this focusing lens, this laser interacts with the target material, and plasma is generated normal to target material. As plasma becomes cooled down, this plasma emits radiation, And this radiation is collected by a spectrometer through optical fiber wire. And finally, this spectrometer is a device which converts these radiations into electrical signals. We say these are the spectral lines we observed here. These radiations, we say these are the characteristic radiations. These radiations have information about this material. So that's why we say these are the characteristic radiations. LIBS 2000 spectrometer. Basically, when we use here LIBS spectrometer, this spectrometer basically is a LIBS 2000 spectrometer. So LIBS 2000 spectrometer consists of different sub-spectrometers which are present here. Their model, their grating, regions as well as their bandwidth. One is known as a LIBS HR1, having grating is 2400, region is ultraviolet, and bandwidth is 200 to 301 nanometer. Second is known as a LIBS HR2, having grating is 2400, and region is ultraviolet, and its bandwidth is 296 to 391 nanometer. And third is a laser HR3. Its grating is 1800 and its region is visible, as well as bandwidth is 386 to 513 nanometer. And there is a four, number is a LIBS HR4, having grating is 1800, region is visible, and bandwidth is 509 to 623 nanometer. And finally, LIBS HR5, having grating is 1800, region is visible, and its bandwidth is 619 to 720 nanometer. So these are all spectrometer consist in a single spectrometer known as the LIBS 2000 spectrometer. Basically, we say this is the 2000. 2000 is basically its model. So laser basically stands for light amplification by stimulated emission of radiation. We use here 4-state laser. So this is a ground state, this is a short-lived state, this is metastable state, this is a short-lived state. So when an electron getting energy from pumping medium, it jump from pumping medium to this short state level. So electron live here less than 10 power minus 8 second, again jump from this point to this metastable state. This radiation decay is the radiationless decay. So from metastable state, electron live here more than 10 power minus 8 second, and finally jump from metastable state to ground state, short-lived state. And here, light emitted, we say this light is a laser light. And finally, electron jump from short-lived state to ground state, and this decay is also fast radiationless decay. This is the data analysis. Emission spectrum of a lithium fluoride plasma produced by the 1064 nanometer laser. Basically, this is the fundamental laser having wavelength is the 1064 nanometer. So this is my data which I observed here in a fluoride sample. So along x-axis there is a wavelength, and along y-axis there is intensity of transition lines. These are the different transition lines. So after verifying, NIST data link is given here. We found these name of these transition line. One is a lithium 1. Basically, lithium 1 represent there is a neutral line. Lithium neutral line having wavelength is a 413.26 nanometer. Second is a lithium 1, lithium neutral having wavelength is a 427.31 nanometer. And lithium 1 neutral lines having wavelength is a 460.29 nanometer. Lithium neutral line having wavelength is a 497.17 nanometer. Lithium neutral line having wavelength is a 610.37 nanometer. And finally, lithium 1 neutral lines having wavelength is a 670.78 nanometer. These are the intensity of each transition line, and this show wavelength of each transition line. So this is the table 1. The emission lines are in corresponding spectral regions of main elements in a lithium fluoride sample. So we found only lithium atom in a lithium fluoride sample, and their particular emission wavelength are given here. One is the 413.26 nanometer. Second is a 427.31 nanometer. Third is a 460.29 nanometer. And fourth is a 497.17 nanometer. 610.37 and finally 670.78 nanometer. So table 2, spectroscopic data of lithium neutral lines observed in a laser produced lithium fluoride plasma. So these wavelengths are we found here, and their transition from upper to lower, statistical weight, transition probability, upper energy. This whole information we collect from this data, which is given here link. So here energy is measured in centimeter inverse. Basically we measure here energy in terms of wavelength. In spectroscopy, energy is measured in terms of wavelength, that is equal to centimeter inverse. So 1 centimeter inverse is equal to 1.239 into 10 power minus 4 electron volt. So this is the relation between centimeter inverse to electron volt. Energy level diagram for neutral lithium. So this is the energy level diagram from upper to lower energy state, which is given here of each elements. Spatial variation in the intensity of the transition line. Basically this is the 3D graph between intensity of a line, distance and wavelength. Here we show that this intensity of each transition line decreases as the distance increases. So this means that as the distance increases, intensity of each transition line continuously decreases. This is the target material. So here, when a laser light interacts with the target material, plasma is generated normal to the target material. So at the center of a plasma, we say that this is a 0 millimeter distance. At a 0 millimeter distance, you show the here line shows here maximum intensity of each wavelength. So as increased distance away from target material, intensity of each transition line continuously decreases. And this is the formula how emission creates. Table 3, the variation of signal intensity versus axial distance of lithium fluoride plasma. Basically, this is a distance from 0 to 2 millimeter. This is intensity, which is measured in a arbitrary unit, and this is the intensity of each transition line. Transition lines are given here. This shows that as the distance increases from 0 millimeter to 2 millimeter, intensity of each transition line decreases. At a 0 millimeter distance, there is a maximum intensity of each transition line. As a 2 millimeter distance, there is a minimum intensity of each transition line. This is a different graph. Spatial behavior of elemental transition lines. We have recorded the spectrum at a different position along the axial position of the expansion of plasma. A variation in the transition lines with respect to intensity and distance is given here. So this is a basically individual graph. This is a lithium neutral line having wavelength is a 413.26 nanometer. This shows that as distance increases, intensity of each transition line continuously decreases. So this is a graph of lithium 427.31 nanometer. As the distance increases, intensity of each transition line decreases. This is a lithium 1 460.29 nanometer. This is a lithium 1 497.17 nanometer. This is a lithium 1 having wavelength is a 610.37 nanometer. This is a lithium 1 having a wavelength is a 670.78 nanometers. And finally, this is a collective graph of each transition line. So this says as the distance increases, intensity of each transition line continuously decreases. This is a basically graph between intensity versus wavelength. Stark broadening profile of lithium neutral line at 497.17 nanometer. This is the one transition line, and this shows that this is the full width of a half maximum of this transition line, which is given at 0.208 nanometer. Here dotted line represents the actual data, whereas solid line, red line, represents Lorentzian curve. So error budget, there is also a fluctuation in the reproducibility of the area data due to following reasons. There may be fluctuation in laser energy measurement. There may be fluctuation in laser length to distance, sample distance. There may be fluctuation in the roughness of surface and geometrical position of a simple surface with respect to laser. This is the conclusion. LIPS technique have been very rapid tool in recent years as well as in commercial along with the industry. So LIPS is a universal method of elemental characterization and much applicable for detection and identification of dangerous chemical and biological substance. So lithium fluoride is widely used in a glass sample, glass windows. In the spatial behavior, we observed the atomic transition line up to distance of 2 millimeter. This is the future plan to calculate the electron number density and electron temperature, to calculate the shift of each transition line, to study the quality of lithium fluoride glass and the verification of local thermodynamic equilibriums and the temporal variation in electron temperature and electron number density of the plasma generated by wavelength. This is a fundamental wavelength. So acknowledgement. I am thankful to foremost my respectable supervisor, Dr. Naik Mohammed Sheikh, Professor in Institute of Physics, University of Sindh, and my co-supervisor, Dr. Wasim Ahmad Bhutto, Assistant Professor in Institute of Physics, University of Sindh, for their suggestions and cooperations throughout this work. I am also thankful to the Dean, Faculty of Natural Science, who provide the opportunity to represent my research work timely. And finally, I am grateful to the worthy Professor, Dr. Javed Iqbal, who gave us the available research faculty in Spectroscopy Laboratory, Department of Physics, Quaid-e-Azam University, Islamabad. So this is the lab view present in Quaid-e-Azam University, Islamabad. This is the power supply. This is a laser source. This is a delay generator. This is the same target material. And this is a reflecting glass. This is a basically focusing lens. And this is a spectrometer. Some pictures inside LIPS lab in Quaid-e-Azam University, Islamabad. These are the some clicks during research work.
Questions and suggestions. Any question, please?
What? I want to study the impurities present in a lithium fluoride. That's why I choose lithium fluoride. And this is a more applicable to make a glass windows. That's why. So if valence electron ejected from a metal surface, this is a photoelectric effect. If the inertial electron transition happen, this is inverse Bremsstrahlung. So because in inverse Bremsstrahlung, there is X-ray emitted. That's why we say this is the inverse Bremsstrahlung method.
Okay, NDR laser, which medium is a pumping? In NDR laser.
ND is a pumping medium, whereas YAG is a lasing medium.
Last step for the G means what?
One is the upper state and the other is the lower state.
NDR and last step YA.
G is for granite. GRNET. This is a basically symbol which is used here, right?
My question is that when an electron jumps from ground state to upper short-lived state, when it comes to from upper short-lived state to metabolite state, so why this region is energy less?
Because there is a collision happening. Due to collision, electron transfers its energy. And there is no collision happening, electron must emit light photon.
Observation
So in my research objective, this is basically motivation.
No, but there must be, when you have started working, you must have the research objectives which you want to achieve it. You did not give it at least to understand whether whatever the research objectives were there, you have achieved those or you have not achieved this one. You are not yet.
So this is the first introductory seminar.
So, Professor.
Bismillah ar-Rahman ar-Rahim. The chairperson of the Department of Physics and also today's the scholars supervisor and and there are other research scholars and the students. This Assalamu alaikum. This today we listened to Dr. Saifullah Jamali, who talked about spectroscopic analysis of lithium fluoride samples using laser ablation. And he gave it some of the work, and basically he has carried out the work at Islam Qaeda Azam University, most of this one. I have requested, I have suggested the professor that if you involve the scholar where the work is being conducted, then the quality of work will slightly improve because he will take more interest in the student. But this is generally human behavior, that because if you are involved with something, then this is give more time to this one. But that is depends upon the department and their own arrangements. But this is a first seminar, and we generally ask the questions only just to evaluate the background knowledge of the student, and another is how he is going to respond to the questions, and another is the originality of the work. That's why this has nothing to do with your seminar. This seminar is just a type of the trainings, and if you will agree, we allow him to continue his work, and hope he will do it slightly better in the next seminar. And with this one, we congratulate the scholar and his supervisor for today's work. Thank you very much.
From higher state to lower state.